Welcome to all. I am Nagaraj N, Assistant Professor, Department of Physics, Government Postgraduate College, Kolar. And this is about Bangalore North University, third semester BSc Physics, topic electricity and magnetism. And these are the learning objectives of the session. Here one can understand the decay of charge in a series LCR circuit, expression for charge in LCR circuit with condition for overdamped, critically damped and underdamped. And these are the learning outcomes of the session. Students can understand the transient response of LCR circuit for discharging of charge, analyze the transient behavior of LCR networks for various conditions, can see the nature of graphs for underdamping, critically damping and overdamping. This is the decay of charge in LCR circuit. The circuit consisting of an inductor L, capacitor C and resistor R, all are connected in series with a battery of EMF E and two keys 1 and 2. At any instant, the applied voltage is partially utilized in overcoming the back EMF in the inductance, partially utilized in the resistance as a potential drop, and the rest is used in charging the capacitor. When the key 1 is closed for some time, this is a key 1, it is closed for some time, the capacitor charged to Q0. Next, when the Q1 is released, and at the same time 2 is closed, this 2 is closed, the capacitor discharges through an inductor and resistor. And we know the definition of current, I is equal to dq by dt, and if you apply the Kirchhoff's voltage law in this network, the voltage across, sum of the voltage across the inductor, capacitor and resistor is 0. So this is a LdI by dt is the voltage across the inductor, and IR is the voltage across the resistor, and Q by C is the voltage across the capacitor. The sum of these three is equal to 0. And if you apply I is equal to dq by dt, this equation becomes L into d square q by dt square plus R into dq by dt plus q by c, that's equal to 0. If you divide this whole equation by L, then it becomes d square q by dt square plus R by L dq by dt plus q by LC is equal to 0. Take R by L is equal to 2b and 1 by LC is equal to k square, then the previous equation becomes d square q by dt square plus 2b dq by dt plus k square q is equal to 0. This is a differential equation, and the solution of this differential equation is of the form q is equal to a e to the power of pt. If you differentiate this equation with respect to t, we will get dq by dt is equal to p into a e to the power of pt. And if we differentiate it again, you will get d square q by dt square is equal to p square a e to the power of pt. Substitute this dq by dt and d square q by dt square in this equation, that means in the equation number 2, we will get p square a e to the power of pt plus 2b pa e to the power of pt plus k square a e to the power of pt is equal to 0. Take this capital A is common, so then this equation reduces to p square plus 2b p plus k square is equal to 0. This is a quadratic equation of p. The solution of this quadratic equation the roots of this quadratic equations are p is equal to minus b plus or minus root b square minus k square. That means this equation has two roots. One is minus b plus root b square minus k square, and another one is minus b minus root b square minus k square. Therefore, the solution becomes q is equal to a into e to the power of minus b plus root of b square minus k square into t plus b into e to the power of minus b minus root b square minus k square into t. And this is the definition already we have chosen, I is equal to dq by dt. So if you differentiate the previous equation, so you will get this equation. So you will get this equation. Then take t is equal to 0, that means in the beginning, then q is equal to q naught and I is equal to 0. Then if you apply this condition, then the fourth equation, the previous equation becomes a plus b is equal to q naught, and this equation, equation 5 becomes minus b into a plus b plus root of b square minus k square into a minus b, that's equal to 0. Or a minus b is equal to b into q naught divided by root of b square minus k square. So here we have two values, two equations, a plus b is equal to q naught and a minus b is equal to b q naught divided by root of b square minus q square. If you solve these two, you will get a and b. A is equal to q naught by 2 into 1 plus b divided by root of b square minus k square, and b is equal to q naught by 2 into 1 minus b divided by root of b square minus k square. So if you substitute this a value and b value in the equation number 4, if you substitute 8 and 9 in 4, you will get q is equal to q naught, and this is a value, e to the power of minus b plus root of b square minus k square t, plus this is a b value into e to the power of minus b minus root b square minus k square into t. This is the expression for decay of charge. Now, when b square is greater than k square, b square is equal to greater than k square, then r square by 4l square is greater than 1 by lc. The discharge, the charge decreases exponentially. That is shown in the curve here. So this is this curve. When b square is greater than k square, the charge decreases exponentially, and this discharge is known as non-oscillatory. This discharge is known as non-oscillatory, that you can observe in the curve 1. Next, when b square is equal to k square, then r square by 4l square is equal to 1 by lc. The charge decreases exponentially in shortest time. So that you can observe in this curve 2. And this represents critically damped discharge. So this represents the critically damped discharge. Next, when b square is less than k square, then this root of b square minus k square is an imaginary. Hence, root of b square minus k square is equal to I root of k square minus b square, or if I take minus is common inside the bracket, you get root of minus of k square minus b square, where root of k square minus b square is a real. So then the previous equation, equation 10 becomes q is equal to q naught e to the power of minus bt e to the power of I root of k square minus b square into t plus e to the power of minus I root of k square minus b square into t divided by 2. This is of the form e to the power of I theta plus e to the power of minus I theta divided by 2 plus b divided by root of k square minus b square into e to the power of I root of k square minus b square t minus e to the power of minus I root of k square minus b square into t divided by 2 by. This is of the form e to the power of I theta minus e to the power of minus I theta divided by 2i. So then I am taking this as it is, this constant as it is, this term as it is, q naught e to the power of minus bt into, this becomes cos of root of k square minus b square t, because e to the power of I theta plus e to the power of minus I theta divided by 2 becomes cos theta. So then this becomes cos of root k square minus b square into t plus, I am taking this whole term as it is, b divided by root of k square minus b square, and this whole term becomes sine of root k square minus b square into t. So then you take root of k square minus b square outside the bracket, therefore q is equal to q naught e to the power of minus bt divided by root of k square minus b square into, there is no root of k square minus b square in the denominator here, therefore it becomes root of k square minus b square into cos root of k square minus b square t plus this b as it is, I am taking as it is, b into sine root of k square minus b square into t. Take cos theta is root of k square minus b square divided by k, and sin theta is b by k. So then this becomes root of k square minus b square is equal to k into cos theta, and b is equal to k into sin theta. If you substitute here, and if you take k is outside the bracket, then q is equal to k k q naught e to the power of minus bt divided by root of k square minus b square into cos theta cos of root k square minus b square t plus sin theta sin root of k square minus b square t. This is of the form cos a cos b plus sin a sin b. Cos a cos b plus sin a sin b becomes cos a minus b. Therefore, this becomes q is equal to, I am taking this whole term as it is into cos of root k square minus b square t minus theta. This equation shows the discharging is oscillatory, and that you can observe or you can see in the curve 3. The amplitude of oscillation diminishes exponentially. See, the oscillation keep on decreasing exponentially on account of the term e to the power of minus bt. And if r is very small, if this r is very small, the oscillation persists for a long time. When r is 0, the oscillations are continuous. And the frequency of oscillation f is equal to root of k square minus b square divided by 2 pi. If you substitute the k square value, b square value, will get this equation f is equal to 1 by 2 pi root of 1 by LC minus r square by 4l square. This is the natural frequency of the circuit. The condition for oscillatory discharge is this. Then the oscillation just stop when r is equal to root of 4l by c. Further, if the resistance of circuit is 0 or negligible, then f is equal to 1 by 2 pi root of l by c. So this is the conclusion of this session. So we can study the discharging capacitor in LCR circuit, solving the differential conditions like over-damped, critically damped and under-damping, and the graphical representation. And these are the resources we have taken. Thank you very much.